this video in which I will be uh, showing you the first demonstration of MPI and explaining the first program of MPI, which incorporates all the basic building blocks of MPI, the main routines that allow you to create a very basic Hello World program in MPI. Okay, so we'll be covering this point here, and then during the next weeks, we'll be talking about the communication routines, point-to-point communication and collaborative communication routines in MPI. So a simple communication model in MPI would be as follows: to create a certain first process that sends a piece of data to another process that does some certain calculation on it. It has to receive that piece of data that does certain calculation, and then it has to do the same thing to send the data to the first one so that first process would display the final result to the end user. So to achieve this, the application needs to specify to the MPI implementation how do you compile and run an MPI application, namely how to run the MPI application by specifying the number of hosts or processes that you have in hand, and how will processes be identified, and how will the data be described while being sent or received. Okay, the data type, the amount of data that you are sending and receiving, etc. So, well, the point number 3 will be part of the of this title, point-to-point communication or end-to-end communication. So we'll see it next time. But the basics of how to declare the processes in the command line, and how to identify the processes and just by doing a basic Hello World program will be done today. So first of all, how to install MPI. As I told you in the previous video, introductory video, MPI is a library. So the applications can be written in C, C++, or Fortran. And Fortran just because it's very known in scientific calculations. So it's still used nowadays in many scientific applications and research projects. It offers appropriate calls. Actually, the application can make appropriate calls to MPI routines where required. But for these calls to take place, you need to import the MPI library and to have a certain implementation installed on your machine. I will give you here how to install the MPICH implementation of MPI. You can write these 2 lines of commands under Ubuntu, and then bingo, you will have it up and running. To test your installation, just run MPICC version, which is the compiler of MPI code, and MPI exec minus version, and just to have an idea about the installation location and how this, whether this has been successful or not. And then you can try out the Hello World program that is given below. But before giving you the code, let's talk about how you would run the compile and run the code. Well, for regular applications, you use GCC, you write your C program file name, and you write -o, and you specify a certain binary file as an output. And then you run your file in this way. You type / your output file name. In MPI, you use MPICC instead of GCC, and then but you keep on the same arguments. And then instead of typing /test, you have to write MPI exec and then your file output file name. But in addition, you have to specify at this moment, statically at this moment, the number of processes that you want to allocate. Okay. So know that MPI run also works, and that the option -np is similar to -n. So just in case you see them somewhere in the online tutorials that you may find here and there, and note that other command options will be shown for execution on a cluster of nodes below. So for C programs, you can use the MPICC, and for C++ program, you can use MPICXX. So just in case you want to use C++ syntax in your application, and in this case, maybe your file is having the CPP extension. To link external libraries, such as the math library, you can add their options in the MPICC command line. And you can just assume that actually MPICC, as you may have noticed, is like GCC or like G Fortran if you were running your Fortran code. If you want to run on multiple hosts, you can just specify the number of hosts, or you can also specify which hosts do we have, and assign to each host a particular number of instances. Okay, so here we have 16 all in all, but that you are dividing into fours on the multiple hosts. In this case, the first four processes run on H1, the next four processes run on H2, etc. However, if you just specify the particular number of hosts that you want to run over, well, in this case, you can the runtime environment of MPI will run the first process on H1, the second on H2, etc., so that it wraps around, so that H1 will also have the fifth, and then the ninth, and then the 13th processes. Well, actually, which command line to use, or which distribution you would use, well, it all depends on the code that you wrote in your program, and how you are distributing the chunk of data over the multiple processes, and whether these chunks are easier to read by process number I or J, etc. Okay, so it depends on the location of your data and whether it's easier for certain hosts to read certain chunks of data. So if you know already that, let's say, the first four files, so imagine that each process is working on a certain file. You have 16 different files in total, and you have the same piece of code that goes into these files and open them. Imagine these are database files, for example. So if you know that the first four database files exist on host number one, the next four files exist on host number two, etc., well, you need to use this format in this case. If you know that they are distributed in this way below, then you need to use this line. Okay, if it's a combination of these, well, you have to be very careful about how you open your files, you access them, and you share the data between the multiple processes that you have. If there are many nodes actually, and you don't want to specify this on the command line, well, you can actually define a host file, HF, and you can pass it as a parameter. Inside your host file, you can specify all these particular settings. And of course, the name of these hosts should be defined in the host file of your operating system. How do you identify processes? Well, actually, before identifying a particular process, you have to identify its rank in a certain communication group. So there is this concept in MPI that you have to understand from the beginning. Okay, so MPI processes can be grouped into or collected into groups. Each group can have multiple colors, sometimes called contexts. A group plus color would define a communicator. You can think about it as if it was a channel of communication. So it's like a name for the group. And for the same communicator that includes or involves a certain subset of the total set of processes that you have in hand, you can have multiple names or aliases. Okay, so let's understand this. We will have a diagram on the next slide that will clarify all these details. But just to show you what is the role of the communication group or the communicator, when an MPI application starts, the group of all processes is initially given a predefined name called the MPI communication word. Okay, so it's the whole set of processes. The same group can have many names, but simple programs do not have to worry about multiple names, okay? And usually even in simple programs, we only use the MPI word, okay? So we don't create multiple communicators so often. I think maybe in this whole course, we won't use other than the communication word, okay? So maybe in the project, sometimes the students would add a feature by creating several different communicators or communication words, okay? So inside each communicator, the a process is identified by a unique number that is called the rank. And there is a function or a routine to get the rank. So we have a function to get the number of processes inside a certain communicator, and we have another routine that would get you the rank of the process inside that communicator. So for two different communicators, the same process can have two different ranks. So the meaning of rank is only defined when you specify the communicator. This is why the function that gets the rank would take as a parameter the communicator. Okay. Let's see this in a diagram. So suppose you executed your code on 16 different machines. Okay. So you will end up having 16 different processes. They all belong to this predefined communicator, as we said, that is called MPI word. Until now, la vie belle, everything is fine. And I think this is the standard. This is what you need to know, and this is what you will see and what you will use in 99% of the course. But you should also understand, just in case you find other pieces of code, that you can create, first of all, different aliases for the same communicator, okay, or communication channel. So in this case, you can create a different alias. So just in case you don't want to use the MPI word name, you can create another alias to you can call this communicator uh, my the total number of processes, or my whole set of processes, okay? Or you can call it everyone, or every process, okay? You can create another alias too. And actually, you can create communicators that do not contain all the processes in the system, unlike the MPI word, okay? In this case, actually, every process in the communicator has an ID that we call the rank. For example, if this is the first process to add, this is the second one, third one, fourth one, etc., then they will have these ranks from 0 to 7. Okay. Why would we create a particular subset of communicators inside the MPI word? So maybe because we want these processes to work on a certain moment during the whole lifetime of the process on, I don't know, on analyzing the left-hand side of a certain image, and to leave the other processes to work on the right-hand side of a certain image if they were doing image processing. Okay, or maybe we want them to access a particular database file, or we want them to do a particular task together. So we can create custom communication channels just for these purposes. But actually, you can arrange your processes in different ways, okay? Depending on their network addresses, depending on the files that they have shared together, etc. And as you may have noticed, certain processes may have different names and different IDs or ranks inside each communicator. So, for example, these processes or these machines had ranks 1, 2, 5, 6, okay, in this communicator, but in the following one, they are having different IDs or ranks 2, 3, 4, 5. So the communicators can be created by hand or using the API provided by MPI. You can check here the code. And simple programs typically only use the predefined communicator MPI word, as I told you, so you don't need to worry too much about the communicators. Okay, it's something that we have to explain to you once for all, so that you get an idea why do we have this MPI com word, and why do we need to refer to it when we have a default setting where we only specified a certain number of processes and we want to refer to one of them. So let's see how do we identify processes inside the MPI program. So to write your most basic MPI program, you need at least to include the MPI.h library. You need to call MPI init, and you pass to it the argc and argv parameters that you received from the command line. And you have also to call MPI finalize at the end. So these are the basic requirements. If you do nothing else, you won't see anything displayed on the screen. You won't feel that anything happened, but at least you have to trust the library and to know that MPI has been initialized and then it has been finalized. Okay, so the minimum pieces of code that you can add to see something on the screen are the following. You can ask MPI to give you the rank of your current process among all the other processes that exist in the MPI com word. To fill in the rank for you, you have to provide the address of a certain integer. Okay, so you have to provide the address of this variable here, integer variable. Okay, so why? Because this function takes a pointer on an integer. Okay. The other function is the MPI com size. You also have to provide a communicator name, and you can ask the MPI library to fill in the size for you in this size variable. So it's another function that takes a pointer towards an integer, and it would fill in that integer for you with the right number, which designates the size of your communicator or the number of processes in your communicator. So this is your way of knowing what has been typed on the command line. If the end user typed -n16, then you would get 16 in this variable here. If they typed -n8 or 32 or whatever, you will get that number inside the size, okay? Particularly because you asked about the size of the MPI com word, okay? So the size or the total number of all the processes, okay? So you are writing a program here and you don't know what the end user has typed on the command line. So the only way to get it is through this function call. How can you try to visualize something on the screen to see if 16 different processes have been really created? Well, you can type this basic message. I am the process number something, number an integer, among the total size that has been read here, okay? We will see this code live in a couple of seconds. Sorry, in a couple of minutes. So if you want to print actually the size only once, okay, well, you can delegate this to one particular process. For instance, if you're, even if you only have one process, well, this would exist and would be of rank 0. So you are always sure that such a process exists. And typically we call it the master process, okay, or the master task. So you can make this check. If the rank is equal to 0, then print off this message here. You can guarantee in this case that this message is printed only once. Another component that you can add to this basic program is to get the processor name. It's kind of the machine name, okay, to just in case you want to display something coming from different machines, well, you can use the name of the machine on the network, okay? You will see that if you run this code on one single machine, well, it will be the same machine name on all the lines. But how to get the name of the machine? Well, you have to do a certain maneuver. You have to declare an array of size this constant. So there is a constant called MPI max processor name that designate the number of characters, the maximum number of characters that is used by MPI to specify the processor name or the machine name. So maybe the machines can have names up to, I don't know, let's say 256 characters. Well, MPI does not recognize this. Maybe it will truncate this name down to a certain fixed number. It depends on the specification and on the implementation. So maybe it will cut it down into 10 or 16 or 8 characters, something like that. And this is why we have to use this constant. And then we can fill in the name here. But since the array is larger than what you need, then you can use actually another integer, okay, and pass its address to this function called cat processor name, so that it fills in the name for you, and it specifies also for you the number of characters that have been read from the machine to designate its name. And in this case, you can actually know the exact number of characters designating the name of your machine. Okay, well, if you display your variable using the percentage s inside printf, you only need to specify the name variable. You don't need to specify the name length, okay? Because inside the name array, you will have all the characters designating your machine name, and then at a certain moment, the null variable \0 and maybe certain garbage characters afterwards that are meaningless. Okay, so suppose your machine is called I don't know, API, okay? So we'll have these 3 letters and then \0 afterwards, okay? So this is sufficient for the printf function to know that the name stops here. But if you need to know the exact number of characters, then in this case, 3 will be stored in the name length variable that you pass to the get processor name. Okay, one last word before we see the demo together. For a graceful exit of all the processes, you need to call MPI finalize, and you should do it really at the end. In this case, each process will terminate its work correctly and gracefully one after the other, and no one will interrupt the work of another one. But just in case you catch a certain error, and in that case, the process that has the error decides that it's useless for the other processes to continue their work. And in order to prevent the end user as soon as possible, you can write this piece of code. You can write MPI abort. You can specify the communicator that you want to abort, and then you can pass the error code. In this case, this will make a best attempt to abort all the other tasks in the communicator set. And it actually currently only works on the MPI ComWord, so you cannot abort a subset of processes from different communicators. It only works on all of them at once. And the error code is usually the return value of the parallel executable in case you want to collect what they have performed. Okay, so in the next videos, we will see the first routine for the message passing and how it can be synchronized. And we'll also see how collaborative communication can be done between the MPI nodes. So let's see these examples in a demo. So I have Ubuntu here, and I have run the installation command. So you can see my commands here. So I have updated my apt-get tool, and I have installed MPICH. So afterwards, I moved to this folder here actually. Oh wait, maybe I have to cd to this location. So of course, if I run MPICC minus version, I will get an intelligible message and not a message saying that MPI is not installed on my machine. Afterwards, I can switch to this location, particularly to this one, ls-l to see my pieces of code. Yeah, and here we have the MPI hello.c and hello2.c. So let me see these pieces of code with you. So the MPI hello.c has the following code. I have the MPI init, so I have the include MPI.h. I have an MPI init. I'm getting the rank from the MPI com word. I'm checking the size. It means the total number of processes that are running and the current ID of the process. And then I'm displaying a message to say hello from the specific process among the total number of processes. And then MPI finalize is called. And let's run this program. So I can call MPI CC on hello, MPI hello .c with an output in MPI hello. If you get to the next command line without any issues, then it means that your code is pure and everything is fine. Now I can run my code using MPI exec or MPI run with -n, and I can specify, let's say, 4 different nodes, and I can specify my file, my binary file ./MPI hello. Let's run it. Well, you will see a hello message from each of the created processes, 4 created processes. You can notice that the first process has finished its execution really at the end after the 3 other processes. Okay, so don't forget that here I don't have an effective network and multiple nodes. I'm just running on my computer, and then and hence actually the MPI library is simply using the multiprocessing capability of my machine to perform this juggling between the processes and the computing tasks. So let's run once again. Here I see them in order. Okay, 1/3 time. Okay, so sometimes you see it a little bit stagnant, but then you have to run multiple times. Or maybe you can also increase the number of nodes. So let's switch to 16 different nodes, and then I'm quite sure that you will see an out of order execution of your processes, and this shall give you a strong feeling about the effective parallelism that is taking place inside your code. Let's switch to the second example of code, which is the MPI hello number 2, in which after initializing the MPI environment, well, actually we can pass null here, or we can also pass the argc and argv as usual. We are taking the word size from the MPI com word, and then the word rank in this variable, and then we are also getting the name of the machine. So we're doing this fancy operation by getting the name of the processor. It means the name of the machine. My machine is called the Bilal PC or something like that. And then finally, we're printing off the hello message from the processor name, word rank among the word size. And we are finalizing the MPI code. Okay, so that's it. So let's see the result of this code. So let me call MPI CC, but this time on MPI hello word number 2. It seems no errors in the compilation are taking place, so everything is fine. And now we can run our code, let's say, on 4 machines at first. So we see here hello world from processor with this name, which is the name of my machine, rank, given rank out of total number of processes. Okay, and we can also switch to 8 different nodes. So here we see that maybe they are rather in order, but we can actually try to run several times until we get an out of order run. So here we see the process number 0 finishing at the end, or we can simply increase the number of nodes as I did in the last example. And then most probably you would see an out of order execution of your code. Okay, so that's it for this video, and see you on Friday. See you on the next session on Friday to discuss all these details and to further elaborate on the end-to-end communication and collaborative communication. Thank you for listening, and see you soon.